Welcome to Naradar Academy. In this video, we are going to discuss about point estimation and interval estimation. So here I am going to give you all the concepts about point and interval estimation. Problems will be discussed in a later video. In sampling distribution, see we have two things now. One is population, which is the collection of all items under study. The another one is sample. Right? Sample means it is randomly selected elements from the population. Right? Okay, so both population and sample have their own mean, median, mode, variance, etc. And sample also, it has its own mean, median, mode, variance. The measures of the population are called parameters and the measures of the sample are called statistic. Okay, right. Now, sample is very small in size, which we have taken from the population. So, we can calculate the mean, variance, any other measure if we want to compute, we can compute it easily from the given sample. But for the population, it may be difficult for us to identify. So, what we do is from the known statistic values, that is from the sample mean or sample variance, we try to find out the population mean and population variance. There are two such types. One is point estimation, another one is called interval estimation. Point estimation means if the sample mean is known, then I find an approximate estimate for a population mean. Okay, so that a single value I find from the sample mean, I find a population mean through approximation, and that is called what? Point estimation. Interval estimation means sometimes I may not be able to find out what is the exact mean of the population. In that case, I can find out in which interval the population mean will lie. That is called interval estimation. Let us discuss one by one. Okay, first let us start with point estimation. See, when we use the value of a statistic means what? The measures of the sample. To estimate a population parameter. Population parameter means measures of the population. It is called a point estimation. Okay, point estimation means, see, simply when we calculate the population mean or variance from the sample mean or variance, it may or may not give you the exact value, isn't it? So, in order to check whether they will define the population correctly or not, we have certain characteristics. One is unbiasedness, another one is efficiency, another one is sufficiency. Okay, and few more things are there. Consistent estimator. Okay, like that. So first let us see about unbiased estimator. The first one is what? Unbiased estimator. A statistic theta cap is an unbiased estimator of population parameter theta if and only if expectation of theta cap equal to theta. Hope you understand this one. That is theta cap. For example, suppose let me take this is the mean of a sample. Okay, the mean of the sample is an unbiased estimator for parameter theta. That is mean of the population if and only if expectation of theta cap equal to theta. Right? If this is the condition you have to remember. Unbiasedness means what? Expectation of theta cap equal to theta. What is this theta cap? Mean of the sample. And what is this theta? Mean of the population. Okay. So expectation of theta cap equal to theta. If this condition is satisfied, that estimator is said to be what? Unbiased estimator. Okay. Now let's see some example. If we have a binomial distribution, X is a binomial distribution following random variable with parameter n and theta. Okay, n means what? Number of trials, and theta means what? Success, probability of success. Then the sample proportion x by n is an unbiased estimator of theta. So what is an unbiased estimator for theta? X by n, right? Because expectation of x by n is equal to what? N is a constant, no? So 1 by n into expectation of x. But expectation of x is equal to, in case of binomial distribution, expectation of the random variable is equal to n into theta. So n get cancelled, so simply we get theta, isn't it? So what we get? Expectation of x by n equal to theta. Therefore x by n is an unbiased estimator for what? Binomial distribution. Next one. When theta cap is a biased estimator of theta, what do you mean by biased? If it is not unbiased, it is said to be biased. Biased means it is deviated from expectation of theta cap. If expectation of theta cap is equal to theta, it is called unbiased. If it is not equal to theta means it will deviate, no? That deviation is called what? Extent of bias. That is denoted by B of the theta. B for bias. Okay. B of theta equal to expectation of theta cap minus theta. In case of unbiasedness, this B of theta will be 0. If it is non-zero, that value is called what? Biasedness. Okay. Suppose if limit n tends to infinity beta of theta, b of theta equal to 0, then the estimator is said to be asymptotically unbiased. So unbiased means expectation of theta cap equal to theta. Asymptotically unbiased means what? Limit n tends to infinity b of theta equal to 0, right? If x1, x2, etc. xn constitute a random sample from a uniform population. Uniform population we know, no? With alpha equal to 0, then the largest sample value is a biased estimator of the parameter beta. See, largest sample value. Yeah, this is a discrete distribution. No, you take the largest sample value. That is a biased estimator for parameter beta. N plus 1 times the largest sample is an unbiased estimator. Okay, and 2x bar is also an unbiased estimator of beta. So they have given estimator for beta. One is largest sample value, it is biased estimator, and n plus 1 by n times the largest sample unbiased, and 2x bar is an unbiased. So three things they have discussed for uniform distribution. Next one, S square is the variance of a random sample from a infinite population with variance sigma square. Then expectation of S square equal to sigma square. This is another important result. That is sample variance of an sample variance is an unbiased estimator of an infinite population. Okay, this is sample variance. This is an unbiased estimator for the population variance in case of infinite population, but not for a finite population. Here I have given. So for regarding variance, if the population is infinite, sample variance is unbiased for population variance. If it is from a finite population, it is not an unbiased estimator. Okay, next one. If we have to choose one of several unbiased estimators of a given parameter, we usually take the one whose sampling distribution has the smallest variance. See, for a given estimator, no, that is we may have several unbiased estimator. The unbiased estimator need not be unique. We may have, that is for mean itself, we may have mean, median, mode, all of them may be unbiased estimators. But among, if you have several unbiased estimators, which one will be the best suited for your population? So for that, what we have to do is we have to choose the one which is having the smallest variance. Okay, if we have many number of unbiased estimators, which one will you choose? The one having the smallest variance. So the small variance is given by means of Cramer-Rao inequality. If theta cap is an unbiased estimator of theta, and variance of theta cap is given by 1 by n into expectation of dou by dou theta of log f of x the whole square, then theta cap is a minimum variance unbiased estimator of theta. This is the minimum variance. This is the minimum variance given by an unbiased estimator. So this formula is important for selecting an unbiased estimator in case where you have many unbiased estimator for a given theta, right? Next one, x bar is a minimum, that is MVUE means minimum variance unbiased estimator. Okay, x bar is a minimum variance unbiased estimator of mu of normal population. That is, if you have normal distribution, then sample mean is a minimum variance unbiased estimator for mu, mean mu also. Okay, then x bar is a minimum value unbiased estimator of mean of any population. Here first I have stated for normal population, then for any population, x bar is a minimum variance unbiased estimate for any population. Next, if theta 1 cap, theta 2 cap are two unbiased estimators of parameter theta of a given population, and variance of theta 1 cap is less than variance of theta 2 cap, then theta 1 cap is relatively more efficient to theta 2 cap, and the ratio variance of theta 1 cap by theta 2 cap is used as measure of efficiency of theta 2 cap relative to theta 1 cap. See, here what we are stating is, see, you are having so many unbiased estimators, among which you are going to choose only the one which is having the minimum variance. That is the best suitable. Okay, right? Now you see, I am having two such unbiased estimators. Among them, right? Among them I am having the least variance. Okay, the least variance you keep fixed the unbiased estimator which is having the least variance. Then if you want to find the efficiency of the other unbiased estimators, okay, only the minimum unbiased estimator you are going to prefer. But if you want to compare it with the other unbiased estimators, you have to find the ratio of variance of theta 1 cap by variance of theta 2 cap. Okay, this will give you the measure of efficiency of the other unbiased estimators. Understand? Okay, so far what are the things we have seen? First one is what is an unbiased estimator, and then what if it is not unbiased, what is the biasness of the estimator? Okay, and what do you mean by asymptotically biased, asymptotically unbiased, sorry, asymptotically unbiased estimator? Then suppose if you are having so many unbiased estimator, then in that case which one will you choose? Which is the one having minimum variance? That is said to be the minimum variance unbiased estimator. And now we have seen if you have so many minimum variance, if you have so many unbiased estimators, how to find the efficiency of an unbiased estimator with the minimum variance unbiased estimator. That is given by ratio of variance of theta 1 cap by theta 2 cap. Okay, now one example, when the mean of a normal population is estimated on the basis of random sample of size 2n plus 1, then the efficiency of the median relative to mean. See, here the population is a normal population. I am going to find a estimator for mean. Okay, right? Estimator for mean. Right? For mean only I am going to find the estimation. For that I can use either mean or median. Both are there. No, sample mean I know and sample median I know. Both can be unbiased. But which one is minimum variance unbiased? Obviously mean. Mean is the minimum value unbiased estimator for the population mean. But median is also an unbiased estimator. Then what is the efficiency of median to mean? That is given by 4n by pi into 2n plus 1. This is by applying this formula we have obtained. Okay. What is the size of the population? 2n plus 1. So the efficiency of median to mean is given by 4n by pi into 2n plus 1. Okay, I think from this you can understand, that is for a normal population mean I have two unbiased estimators, one is mean, another one is median, but obviously this is my minimum variance unbiased estimator. So the efficiency of median compared to mean is given by 4n by pi into 2n plus 1. Okay, now this is efficiency. What is asymptotic efficiency? Just you take limit n tends to infinity of this value. So this is equal to 2 by pi. This is approximately 64%. That means for large sample the mean requires only 64% as my observation as the median. That means if your median requires 100 data, your mean requires only 64 of the data for more reliability. Okay, so that is the meaning. That is mean is 64% more efficient than your median. If theta cap is not an unbiased estimator of a given parameter theta, we judge its merits and make a efficiency comparison based on the mean square error instead of variance. If it is not an unbiased estimator, for unbiased estimator we use its variance. For not an unbiased, that is biased estimator, for biased estimator what do we use? That is mean square error, expectation of theta cap minus theta the whole square instead of variance. Okay, so for unbiasedness we calculate minimum variance. For biasness what we calculate? Mean square error, expectation of theta cap minus theta the whole square. Next one, the statistic theta cap is consistent estimator if probability of theta cap minus theta less than c is equal to 1. Consistency is an asymptotic property. Okay, consistency means in the long run only we calculate. So consistency means what? Probability of theta cap minus theta less than c as limit n tends to infinity tends to 1. Okay, if theta cap is an unbiased or asymptotically unbiased estimator of theta and the variance of theta cap tends to 0 as n tends to infinity, then theta is a consistent estimator. This is another equivalent definition. We don't use the previous definition frequently. Only this definition we will use. What is that? What is the meaning of consistency? First, for estimator to be consistent, first it has to be unbiased. Otherwise, asymptotically unbiased. First condition. Second condition, what? Variance of theta cap tends to 0 as n tends to infinity. That is called a consistent estimator. This is another betterment. First, what we do? Find out an estimator. Then we check whether it is unbiased. After that, we check consistent. So, we are moving towards the population parameter with more and more properties. Okay. For a random sample from a normal population, sample variance S square is a consistent estimator of sigma square. Okay, already we have seen this here in the previous section, but there what did we say? Only for infinite population it is an unbiased estimator, but for finite population it is not an unbiased estimator. But when it is taken from a normal population, S square is a consistent estimator of sigma square. Okay, estimator theta cap is said to be sufficient. Next one is what? First unbiasedness, next consistent, now it is sufficient. Sufficient means if it utilizes all the information in the sample relevant to the estimation of theta, that is if all the values of theta can be gained from the individual sample values. Sufficient means no other data is required. That's all. What do we mean literally? Sufficient means what? That is enough, no? That is what we say here. But mathematically, how to prove it is sufficient? See, the statistic theta cap is a sufficient estimator of the parameter theta if and only if for each value of theta cap, the conditional probability, see f of x1, x2, etc., xn given theta cap is equal to, can be written in this form, f of x1, x2, etc., xn by g of theta cap. This is independent of theta. Okay, you have to write it like this. This must be what? Independent of theta. Okay, then that is called what? A sufficient estimator. If x1, x2, etc., xn constitute a random sample of size n from Bernoulli population, right, then theta cap equal to x1, x2, etc., xn by n is a sufficient estimator for theta. Okay, for Bernoulli population, what is a sufficient estimator? Theta cap equal to x1, x2, xn, x1 plus x2 plus xn by n is a sufficient estimator for theta. Next, factorization theorem. This is used for finding the sufficient estimator. While doing the problem, we will be using all these results. The statistic theta cap is a sufficient estimator for parameter theta if and only if the joint PDF, here we have written the conditional PDF. No, conditional PDF is independent of theta. Here if you write the joint PDF, that can be written as product of G and H such that G depends only on theta and theta cap and H depends depends only on x1, x2, etc., xn. No theta should appear in the H term. If this type of factorization is possible, then that is said to be a sufficient estimator. Okay, right. Next, x bar is a sufficient estimator of mean mu of normal population with known variance sigma square. Again, that is the sample mean is a sufficient estimator for the population mean with known variance, that is sigma square. Population variance is known, it is a sufficient estimator. If theta cap is a sufficient estimator of theta, then any single valued function is also a sufficient estimator. That is, theta cap sufficient estimator means any function, single valued function will also be a sufficient estimator. Next one is method of moments. The kth sample moment of a set of observation x1, x2, etc., xn is the mean of the kth powers and it is denoted by mk dash, isn't it? This is the moment. Thus, if a population has r parameters, the method of moments consists of solving system of r equations. Then the next one is method of maximum likelihood. Maximum likelihood is a method to find a estimator. Sufficient estimator yield sufficient whenever they exist, and the maximum likelihood estimators are asymptotically minimum variance unbiased estimator. Okay, right. So if x1, x2, etc. up to xn are the values of a random sample from a population with parameter theta, then the likelihood function L of theta denotes the likelihood function. L of theta equal to the joint PD of f of x1, x2, xn theta. The method of maximum likelihood consists of maximizing the likelihood function with respect to theta. So what you have to do, you have to maximize this function with respect to theta, right? So this will give you what? This will give you a sufficient asymptotically minimum variance unbiased estimator. Okay, right. Now maximum likelihood estimator need not be unbiased, right? And maximum likelihood can be used for simultaneous estimation of several parameters. Okay, right. So that's all about what? Point estimation. Next we are going to consider interval estimation. So interval estimation, already I told you, if you are not able to specifically point out the population parameter, we find it in terms of intervals. So here we use three things. One is what is the interval in which it lie, and another one is what is the level of significance or degree of confidence. Okay, usually we use 95% confidence interval. Right, now let us see some of the statistic which we use for problem. First one is proportion. Proportion means in that case we use this parameter, that is we use this test statistic z equal to x minus n theta by n theta into 1 minus theta, where n denotes the sample size and theta denotes the proportion. Okay, right. So for this is the test statistic which is used, then we compare it with the table value. Okay, these things are only depending on the table value you conclude. This is the only thing you have to remember here. Z equal to x minus n theta by root of n theta into 1 minus theta. This is for estimation of proportions. Next, for estimation of difference between proportions, two proportions are given, no? In that case, we use the statistic, same z equal to theta 1 cap minus theta 2 cap minus theta 1 minus theta 2 by square root of theta 1 by n1 into 1 minus theta 1 plus theta 2 into 1 minus theta 2 by n2. This is for difference between means. Next one is variance, estimation of variance. For that we use chi-square distribution. So here the test statistic is taken to be n minus 1 s square by sigma square, where s square is the sample variance and sigma square is the population variance. Okay, then we compare it with the chi-square table and we say it, whether it accepted or rejected. Next one is estimation of ratio of two variances. For that we use F distribution, and the test statistic is sigma 2 square s1 square by sigma 1 square s2 square, right? And this follows F distribution with n1 minus 1 comma n2 minus 1 degrees of freedom. Okay, that's all. Thank you.